Good afternoon, folks. Happy Tuesday. Hope you're more awake than I am. This is not coffee, unfortunately, it's just water. In case. So it's.
Well, you already had your 3 cups of coffee.
Yes, I had my 3 cups. Yes, I did. And it's not enough. I might have to start going to 4 cups. 11th. All right, let me see if I can find everything. Okay, good. I hope you had a good weekend. I went and saw my daughter graduate, so she's now done with college. I'm sure that you're looking forward to that day too. So it was a lot of fun. All our kids were able to be there, and even my sister and her husband. They're from the Chicago area, but he just got a job with Apple in Sacramento. So they were out there looking for a house, and they came down to Santa Barbara. So that was nice.
Well, congratulations to you, Professor. You are also part of to take some credit for your daughter finishing school.
Yes.
Right?
Yeah, but she wasn't a math major. What's up with that? None of my kids were math majors. Horrible.
Okay.
I failed as a father. Anyway, all right.
Too easy for them.
What's that?
It was too easy for them. They wanted something.
They weren't interested. I'll say that much for them. Okay. Nobody gets scared about what I teach. It's clear, concise, easy to manage. Yeah, well, I will say that on like vacations and stuff, I would do math magic with them. So there's these magic tricks that are math based, and I'm sure that just scarred them for life.
You're rather impressive. You scared them away from math.
Yes, exactly. All right. So anyone have any questions about, say, chapter 6 stuff? I still got to write up some homework problems for you to do based on parametric curves. So I'm going to do that.
Is it going to be on the test, parametric curves?
Parametric curves, yeah.
Are they going to be in the part of the test?
Yeah.
Okay.
They'll be on the final. So we got to do that today, and then we got to review on Thursday then. So that's the goal. And hopefully we can do some parametric surfaces, but we'll see. All right. So any math questions though about stuff? Okay. So let's do some parametric curves. Oh, my goodness. So recall. We had descriptions of curves in R2, right? So this is just different ways of describing curves. We had graphs of functions. 2 of these you're fairly familiar with, right? So, if I have the graph of f of x equals x cubed minus x, I could find out the x-intercepts are at -1, 1, and 0 and 1. And it looks something like that. And that's a curve in the plane. Solutions to equations. And where the only difference between this and the previous one is it's not solved for one of the variables, right? So this isn't solved for y or x. It's x squared plus y squared equals 1. And that's the unit circle, right? And now we have parametric equations. And this is where you get one equation for each coordinate, and they're all given in terms of a parameter. So like one of the equations we saw last time was C of t is cos t sine t. And with parametric equations, there also comes the parameter and limits on the parameter. So remember, that's one way to write it, or a lot of times people will write it separately as my x coordinate equation and my y coordinate equation. And then these are the so-called parametric equations. And t is the parameter.
Pag may inassign ka doon, ko lang.
Siyempre may bayad.
Okay. So, and we saw that this parameterized the unit circle, right? So these are, this parameterized x squared plus y squared equals 1, right? Okay, so I'd like to do a couple of examples where we start with parametric equations and we relate it to Cartesian equations. I'm going to call these things Cartesian equations. Okay. And I guess I'll start with going from parametric equations to Cartesian equations. So example. Find a Cartesian equation for the parametric curve C of t equals 3t minus 2, comma 2t plus 1. And let's say t is from negative infinity to infinity, right? And in order to do this, I'm going to use what's called a technique called eliminating the parameter. And in order to do, and let me show you what that means. You solve for t. So step one is you solve one equation for t. And step two is you substitute into the other. And so inherent in what I'm saying here is that you really have two equations. And that's true when your curve is in the plane. I really just have two equations, right? one for X and one for Y. So if I think of them parametrically, I get X equals 3t minus 2 and Y equals 2t plus 1. So I can solve, say, for t in the second equation. So if this is my first equation, and that's my second equation, I solve my second equation for t, and I get y minus 1 equals 2t, so t is equal to y minus 1 over 2. And now you just substitute that value or that expression for t into the first equation. So I'm going to sub into 1, and then I get something like x equals 3 times y minus 1 over 2 minus 2. And what you notice now is that there's no more t's. Okay, so we've eliminated the parameter, right? That's why it gets this name. And all we have is an equation relating x's and y's. Okay. And hopefully you can see that this is an equation for a line, okay? And we can make it look more line-like if we get rid of that denominator. So I'm going to multiply both sides by 2. And I'll just get 2x is equal to, I get a minus 4 here, and I get 3 times y minus 1 because the 2 in the denominator is eliminated by that 2. And if I just keep solving, I get 2x equals 3y minus 7. Or you might just say 2x minus 3y equals negative 7, something along those lines. And that's the general form of an equation for a line, right? You could solve it for y and get it in slope-intercept form or whatever. That would be fine. The way I usually work with lines is I like this, because if I'm going to sketch it by hand, I can find the intercepts easily by, say, setting y equal to 0. Like if I plug 0 in for y, I get 2x is negative 7, so x is negative 7 halves. Negative 7, so that's negative 3.5, right? So this point is back here at negative 3.5. And if x is 0, then I get y is positive 7/3, so that's 2 1/3. So that goes about there. And what you find is that this parametric curve corresponds to that line. Okay. So this is just an example where we go from a parametric curve, which is we're less familiar with, to a Cartesian equation for a line, which we're much more comfortable with. Any questions about that? Okay, so let's do another similar example. So example, show that C of t equaling 3 cos t 2 sine t for t between 0 and 2 pi parameterizes the ellipse x squared over 9 plus y squared over 4 equals 1. Okay, so I guess like if I were you guys, I don't even know when they teach ellipses or conic sections anymore, but this is an equation for an ellipse. It's similar to an equation for a circle. It's just that you have stretched it horizontally and you've stretched it vertically. So it, rather than being circular, it's elliptical. And in this example, it turns out like if x is 0, then then I can solve, so you ignore this part and you just solve y squared over 4 is 1. Well, then y squared has to equal 4, which means that y is plus or minus 2. So if I'm going to sketch this ellipse, I know that I go up and down 2 units on the y-axis. Similarly, if y is 0, then on the x-axis, I need x squared to equal 9 so that that fraction equals 1. So if x squared is 9, then x is plus or minus 3. And I just, even though you probably remember it, I just want you to believe that what you get is that ellipse. Okay. So we may not be 100% comfortable with this. However, this is at least more familiar. We've seen Cartesian equations that look like this before. And at some point in our lives, somebody told us, hey, that's an ellipse. So we're totally fine with that. Here is a new way to look at ellipses. And what this emphasizes is how to get from the unit circle to an ellipse. So for instance, with the unit circle, my parameterization was just cos t sine t. So what do I have to do to that parameterization to stretch it 3 units in the x direction and 2 units in the y direction? Well, I just take the x coordinate and multiply it by 3 to stretch it 3 units in the x direction. And I take the y coordinate and I double it to stretch it 2 units in the y direction. So it just makes sense that this is what I get when I start with the unit circle, stretch a certain amount in the x and a certain amount in the y. So that's intuitively why that makes sense. Okay. We can also show it algebraically. We're going to verify that it satisfies, verify that points on C of t satisfy the equation, satisfy the Cartesian equation. By substituting these points in. So here's a point, 3 cos t, 2 sine t. I'm going to take that x coordinate and plug it in for x. And I'm going to take that y coordinate and plug it in for y. It'll be on the ellipse if once I do that, it simplifies to just 1. So by letting x equal 3 cos t, y equals 2 sine t in the Cartesian equation. So for me, the Cartesian equation is this one here. Maybe I should just write that down. So this is my Cartesian equation. And so, and me calling it a Cartesian equation just means that it's using X and Y. So those are Cartesian coordinates. Okay. So if I do that, let's just see what happens. So my x squared over 9 plus y squared over 4 becomes, instead of x, I'll have 3 cos t. So it'll be 3 cos t squared divided by 9. And instead of y, I'll have 2 sine t. So that'll be 2 sine t squared divided by 4. And well, okay, so then if I square this, I'm going to get 9 cosine squared t over 9 plus 2, sorry, not 2, 4 sine squared t over 4. And the 9s will cancel, the 4s will cancel, and I'm just left with cos squared t plus sine squared t. And that's just a Pythagorean identity, and that's just equal to 1. So what this is a nice calculation, okay? It's a nice calculation. It says no matter what t is, if it's any number, no matter what t is, when I plug this point into this equation, I get equality, because plugging it into the left side simplifies until I just get the right side. And that means that every point on C is on the ellipse. So this implies every point on C of t is on the ellipse. And I'm just going to ask you to believe that we get every single point. I haven't shown that given a point on the ellipse, it has this form. So I definitely haven't shown that, but I'm just going to ask you to take it for granted that we really do get the entire ellipse. Any questions about that? So I'm going to just increase that equal sign. And this generalizes, okay? So more generally, a parameterization of x squared over a squared plus y squared over b squared equals 1 is C of t equals and again, what should I do to the unit circle? So let's just take a look at the previous example. So if I had x squared over 9, y squared over 4, this was the parameterization, right? 3 cos t, 2 sine t. The reason I needed a 3 here is because when I square it, it's going to cancel with the 9, right? The reason I needed a 2 in front of the sine t is because when I square that 2, that's going to give me 4, which will cancel, and I'm just left with cosine squared plus sine squared. So if I wanted to parameterize this more general ellipse, I'm going to stick with the cos t sine t. I'm going to stick with between 0 and 2 pi, right? But what do I have to do? This right now would just give me the unit circle. But what do I have to do to the x coordinate so that it'll cancel with the a squareds? What did I have to do here? I had to multiply by 3. How can I look at this equation and know it's got to be a 3?
Would you have to take the square root for
Yes.
the values of before cos and sine?
You have to take, so here I started with the parameterization and gave you the equation. Now on the next slide, what I'm doing is I'm starting with the equation and asking for the parameterization. So you got to start with 9, take its square root to get the 3. So I'm going to start with a squared. So I'm going to take its square root and get a 3, an a here and a b there. Any questions about that? So that'll parameterize any ellipse for you. Okay. So pop quiz, I got a question for you. In the back here, or just on the previous page, I used this parameterization for x squared over 9, y squared over 4 equals 1. What happens if I just change that, the limits on t? So pop quiz, what is c of t equals 3 cos t 2 sine t? But now t is between 0 and say pi over 2. So if I go from 0 to 2 pi, I'm going to get once around, and actually that'll be counterclockwise. So how does that change if instead of going from 0 to 2 pi, I just go from 0 to pi over 2? If you had to guess. What do you think would change if you change the limits? Well, let's find out. Why don't we go to GeoGebra? Go ahead and grab GeoGebra. So open a GeoGebra window somewhere. That's me messing around. That's more me messing around. Here we go. Okay, so let me let S be a slider. And what do I want about S? I suppose I want S to be from 0 to 2 pi. Okay. And now I want my curve. So remember the syntax for curve. You got to give it its x. You got to give it the parametric equations. So that was 3 cosine t, 2 sine t. once you know that, you got to tell it what the parameter is, which is t. And let's say we wanted to go from, and then after that, you got to give it the limits on the parameter. So I want to go from 0 to s. Okay. And you notice that since s is currently 1, this is the portion of the curve from time 0 to time 1. But as you let the right endpoint increase, that's just going to get more and more of the ellipse until you're at 2 pi. Okay, what did I do? That's not really what I wanted to do. Until you're at 2 pi. Right, so you can see that a parametric curve really is the path of a ladybug crawling in the plane, right? And you can even make it, animate it so that you can see that sort of real time. So pop quiz, what do you think is going to happen? So right now it's at 2 pi, right? It goes 0 to 2 pi is all the way around. What do you think is going to happen if instead of 2 pi up here, I'm going to change this to pi over 2? What is that going to do to my picture?
It'll only be the first quarter of it.
Yep, it'll just be in the first quadrant. So if I go 0 to, yeah, so that just means you'll go that far. I don't know what the deal is. Oh, it's the step size is too big or something. I don't know. Step, say 0.01. Then I should be able to get closer. There we go. Okay. So changing the limits on the parameter just restricts what portion of the curve you're going to look at, right? That's sort of the long and short of it. All right. Okay, so now I got a question for you. So I'm going to go back to 2 pi. So we have our ellipse here, right? That's our ellipse. Oh, we're going to change the step size to something really small. Oh, the step is good. Should be good. Okay. This you can see, because it grows as you want it to, you can see that it goes counterclockwise, right? Because here you start at 0 and then the bug moves around and it finally gets over there going counterclockwise the whole time. My question is, how do you change these parametric equations? Notice what GeoGebra does. It takes this syntax and gives you separate parametric equations, one for X and one for Y, right? It's very convenient. It just reminds us that I need an equation for each variable. Okay. How could I get it to go clockwise instead? This is a counterclockwise parameterization. Because if I start at 0 and start going, I go counterclockwise around. How could I get it to go clockwise instead? How would I change these parametric equations to make it go clockwise?
Make it go to negative 2 pi.
Okay, so that's a good question. In my mind, I'm thinking it's not going to like it because typically it does. So for a technical reason, I would say no. Let's see what it does. So it didn't do anything. See, it's not letting me hit return right now. And the reason is this negative 2 pi is bigger than 0, right? I could put the negative 2 pi here and the 0 here.
But that would just go counterclockwise still.
That still goes clockwise. Oh, and then this one's messed up because, anyway, then I would have to do S and 0 again because it's, anyway. Oh, I see. So I'm starting, I don't know what the heck this is doing. So if S is, oh, I see. No, I don't want it to do this. I want it to go, so the right thing to do is to start with at negative 2 pi and then go to S, right? And so that the right endpoint is changing here. And then that goes clockwise. Okay, so no, it's just a technicality about things. It only goes one t, or your parameter has to increase in one direction. Okay, so that's a good guess though. What about how else might we change our parameters? So I'm going to go back to 0 to S. How else might we change our parameters? So not the limits, but actually the parametric equations. Well, this starts by going up, right? So your y coordinate is increasing. You really want it to go down instead, right? Start by going down. How might you be able to change this y coordinate so that it starts by going down?
Make it -2 instead of 2.
Yeah, if you just make that negative, then that is just a reflection across the x-axis. And then indeed, it'll go counterclockwise around, or clockwise around. You could also change the sine and the cosine. So you could make the sine go in your x coordinate and the cosine go in your y coordinate. Oops. I didn't like it. And then, but the difference with this is you're at a different starting point. If you change this, it just starts up at the top up here. Because if you plug 0 in, your x coordinate is 0 and your y coordinate is 2. Anyway, so there's a couple of ways you can change the direction that of your rotation. Any questions about that? Okay, so now we get, so let's write down the answers to this here. This was, you get the first quarter, right? So this is at 3, this is at 2. And you just get that portion of the ellipse in the first quadrant. And then the pop quiz, parameterize the ellipse clockwise. And if you want to parameterize it clockwise, then there's lots of ways to do it. One was just make the y coordinate negative. So 3 cos t minus 2 sine t. And again, t is from 0 to pi over 2. Or 2 pi, sorry. And the other was to switch cosine and sine. Not the 3, you're not switching coordinates. Another one was c of t equals 3 sine t, 2 cos t. So what I mean by that is the coefficient 3 stays in the x coordinate and the coefficient of 2 stays in the y coordinate. It's just the sine and the cosine that switch. And you get that. Okay. Okay, so like to do another example just to make sure we're all on the same page. Parameterize, and we talked about this last week, the line segment from P equals -3, 2 to Q equals 5, -5. Okay, so recall that C of t equaling 1 minus t times p plus t times q for t between 0 and 1 parameterizes the line segment from P to Q. Okay, so that's a quick and easy way to parameterize that, right? So I'm going to think of these as vectors. So C of t is going to be 1 minus t times p, which is -3, 2, plus t times 5, -5. And the limits on the parameterization are from 0 to 1. So this, let's simplify it. Let's get it down to just what is my x component function, coordinate function? What is my x parameterization and what is my y, right? So this will be -3 times 1 minus t, comma 2 times 1 minus t. So you do the scalar multiplication first, plus 5t, comma -5t. And so if we distribute this, I'm going to get -3 plus 3t plus 5t. So that's going to be 8t minus 3. And then I'm going to get 2 minus 2t minus 5 more t's. So 2 minus 7t. T between 0 and 1. Just so we're all on the same page, we can just go back to GeoGebra and just sketch this, right? So I can get rid of that and I can now have my line segment, which is the parametric equations are 8t minus 3, comma 2 minus 7t. And then the parameter is t, and it's going to go from 0 to 1. And you get this line segment. Now, you see that one end of the line segment is -3, 2. And the other end of the line segment is, well, it's 5, -5, which that's what we wanted, right? Yes, 5, -5. Okay. But you may not believe that that actually goes from -3, 2 to 5, -5. It could go the other way. There's two ways a parametric curve can go. So in order to see which way it goes, you can set up your limits by saying, okay, I want S to be from 0 to 1 and T to be from 0 to S. Okay, and then you just look at what happens as your endpoint increases. And you see it really does travel from -3, 2 to 5, -5. Okay. Any questions about that? Okay, I want to do an exponential spiral here real quick as another example of a parametric curve. And I can't remember if I did this last time or not. So example, exponential spiral. I don't think I did. So here my C of t, my curve, is just going to be given by e to the t times cos t, e to the t times sine
Oh,
t.
Professor, the screen isn't showing.
Sorry. Yeah, I forgot. Oh, it didn't. Hang on, it didn't. I didn't give it time. Oh, it says it did. Let's see. Yeah. So here's my exponential spiral. C of t is given by e to the t cos t and e to the t sine t. All right. But notice that this is just e to the t times cos t sine t, right? And let's just talk about this for a minute. What is cos t sine t in terms of a vector? Think of it as a vector. What kind of vector is it? Well, in particular, what's its length? What's the length of the vector cos t sine t? What's the length of any vector? This should not be a mystery anymore, right? It's the square root of the sum of the squares. So that's square root of cos squared plus sine squared. But what's cos squared plus sine squared?
1.
That's just 1. So that's a unit vector that makes an angle of t with the positive x-axis. So this is a unit vector making an angle of t with the positive x-axis. Oh, I should mention that t here goes from negative infinity to infinity. So that blue vector has got to be 1 unit long. And the angle with the positive x-axis is t. And this e to the t, that just rescales it, right? That's just a scalar. So it rescales the vector. So the length of c of t is just e to the t. Rescales, so the length of c of t is equal to e to the t. So what happens as, what I want to do is I want to get an idea of what happens to this as t goes to the ends. What's the end behavior? So this vector is just going to rotate around as t increases. The unit vector just keeps rotating because the angle just keeps changing, right? The angle just keeps increasing. What about the scale factor? As t goes to infinity, what happens to e to the t? Remember what e to the t looks like? It's the Nike swoosh, right? Looks like that. exponential growth. So e to the t goes to infinity. So this part is going to be a unit vector that just keeps spinning around, but it's going to keep getting longer and longer because e to the t goes to infinity exponentially fast. So in particular, you can just see that c of, if I plug 0 in, I get e to the 0 times cos 0. So c of 0 is e to the 0 cos 0, comma, e to the 0 sine 0. The sine of 0 is 0, the cosine is 1, e to the 0 is 1, so you're just at 1, 0, right? As t increases to infinity, this blue, the direction just keeps rotating around, but the length keeps expanding, so you get some exponential spiral going around. What happens as t goes to minus infinity? What happens to the length? What happens to e to the t, which is the length of my curve, the distance from the origin to my curve?
It approaches 0.
It approaches 0. So that approaches 0, and that means as I go to minus infinity, I'm rotating the other direction, but it just spirals around like that. So that's why it's called an exponential spiral. Let's go ahead and look at it on Google, on this other one. So I don't know what I'm going to do with S for now. I'll mess with that later. But this will be a new curve. We want e to the t times cos t, comma, e to the t times sine t. T is my parameter, and let's go -2 dot dot 2, or not dot dot, that's a different comma 2. I'm gonna make this go away. And that doesn't give you much. Oh, so pi is 3.12. So how about we go -5, oops, to 5. What you notice is as you zoom in, it just keeps rotating around the origin. Like if you did, you know, -10 here, you just keep zooming in and it keeps rotating around the origin. And the decay of the distance from the origin is exponential. So this thing just collapses to the origin really fast. And then as you span out, you end up getting this spiral shape that keeps getting longer and longer, right? And it just continues forever indefinitely. But you can definitely, it grows very fast. Okay. All right, any questions about that exponential spiral? Okay, so why don't we take a 5-minute break, come back at 5:00 something, 5:04, and call it good. Welcome back, folks. Hope all is well. Did the break suggest any questions to y'all? No. Okay. Excellent. I want to talk about calculus with parametric curves. So I guess I should share my screen. Let's see. Calculus with parametric curves. And let's just do it in 2 dimensions. It's the same in all. And the main thing is you differentiate parametric curves coordinate wise. So this is definitely the basic idea. And what I mean by that is if C of t is given by parametric equations x of t, y of t, then C prime of t is just given by x prime of t, y prime of t. Easy as pie, right? It's almost like if someone told you how should I, or asked you how should I differentiate, you would just do this, right? So this is I just want to point out that this really is the tangent. This vector, this is the tangent vector to C of t. Okay. So for example, suppose C of t is equal to t squared, say for t between -5 and whatever, between -3 and 3. Then C prime of t is just the derivative of those. And I definitely think of C prime of t as a vector. So I'm going to emphasize that by putting these brackets in here. So it's taking a derivative is easy, and I'll come back and I'll prove this because there's a very nice proof of this fact that you differentiate component wise or coordinate wise. There's a very nice proof using vectors. It really follows from vectors, from what we know about vector addition and scalar multiplication. So this is not a mystery. This is how it works out in practice, right? I just take derivatives 1 coordinate at a time. We can even sketch these, by the way. So let's just sketch C of t and say C prime at 1. Well, C prime at 1 is just the vector 1, 2. I literally just get this 1, 2 from plugging 1 into my equations for C prime. And here's a remark. This is supposed to be a tangent vector. It's only going to be tangent to the curve if, so here's our convention, put its initial point at C of 1. Okay. Okay, so let's finish this. I want to sketch this, and then we'll go to GeoGebra and we'll get like a deeper picture or more robust picture. C of t, the y coordinate is the square of the x coordinate, right? So this really is the curve y is equal to x squared. Because when I plug t in for x, I get t squared for y. So this is just a parameterization of the parabola, your favorite parabola, right? So that looks like this, right? So this is my C of t. C of 1 is the 0.11, right? So that's my C of 1. And according to this, if I just, the vector 1, 2 will be actually tangent to it there. So C prime of 1 is tangent to the curve in the usual sense of being tangent to a curve. Okay, so it's somewhat remarkable that all you do algebraically is you differentiate component wise and you still get a tangent vector to the curve. Okay. So let's switch to GeoGebra and see if we can build something that makes this. I didn't want to do that. Actually, I think I had it. I can't see. Shoot. Okay, so go to GeoGebra, not Riemann sums, just GeoGebra. Okay, so this gives me a new thing. I'm gonna do a couple of things. So we're gonna have our curve is gonna be t comma t squared, where t is the parameter, and it goes, say, from -3 to 3. So that's kind of fixed. Okay. Now I'm going to have a slider, which I want to go from -3 to 3. And I'm going to put the point on the curve. So I want the point s squared. So that's the point on the curve. Now the tangent vector is just going to be 1 comma 2s. So that we calculated, right? The thing is, if I think of it like that, then it's a vector from the origin. Okay, so it's just a point in the plane, so it's a vector from the origin. What I really want is I want to put the initial point at A, so I don't want to see B. What I really want is the vector that goes to, that has its initial point at A, and it goes to A plus B. And that's the vector U. It's from A to A plus B. And how do you, so if it's between 2 points, how do you find its coordinates? It's always terminal minus initial. So if it's A plus B minus A, this vector we're looking at is just B. I've just translated the whole picture by A, that's all. So instead of from the origin to B, I'm going from A to A plus B. Okay, and all I'm trying to convince you of is this vector B is always going to be tangent. So you can just play with the slider. You notice that it does change length, right? Definitely changes length, but it's always tangent no matter where we are on the curve. That's just going to give us a tangent vector to the curve. That is not a proof that it's a tangent vector. That is just an example that it's a tangent vector. Any questions about that? Okay. Okay, so let's go back to and let's just get do a couple more examples. So first example, parameterize the circle centered at the origin. Radius 2. And I want a quick and easy way to do it. Okay, so I just want to, I don't want to think too hard. So I'm going to go back here a couple of slides, and we know how to parameterize an ellipse where you stretch by A in the X direction and B in the Y direction, right? This is the parameterization that does it. Well, suppose I wanted a circle radius 2. How far am I stretching in the X direction? How far do I go out in the X direction? From 1 to 2. So I'm stretching by 2. And the same in the Y. So that means that both those should be 2. Both those coefficients should be 2. So parametric equations for the circle radius 2 is just 2 cos t, 2 sine t. And t is between 0 and 2 pi. Okay, so now suppose I want to parameterize the tangent line. To c of t at, say, t equals pi over 3. So I'm trying to parameterize a line now. And I want to recall that the line through P in the V direction is parameterized by L of t equals P plus T times V. Right, the whole tip to tail, it's got to go through P. So if that's my point P, there it is. And in the V direction, so maybe that's the V direction, right? To parameterize the line, I'm just going to take all scalar multiples of V to stretch back and forth. But notice they all have to start at P. So if everything's starting at P, it's not just the scalar multiples. You got to add P to it. And that's why you get the P plus TV to get this entire line. Oop, that line does not look good, but that's my L. So we talked about that last time, that's if you need those two pieces of information to parameterize a line, it's got to be, you need a point on the line and a vector in the line. So if I want to parameterize the tangent line to this curve, right? So this is a recall. Let's just draw a picture. And at pi over 3, I'm right here, and I want the tangent line there, right? So I need the point, and the point is just going to be c at pi over 3. And I need the tangent vector, and the tangent vector is going to be c prime at pi over 3. And that'll give me my 2 pieces of information. Once I know the point and the tangent vector, it's just going to be p plus t times v. So our point P is going to be C at pi over 3. And that's equal to 2 times the cosine of pi over 3, 2 times the sine of pi over 3. And now you remember, cosine of pi over 3 is a half, so this is just 1. Sine of pi over 3 is root 3 over 2, so that's, you're multiplying by 2, so it's just root 3. My vector v is going to be c prime at pi over 3. So I need to know what c prime of t is, right? And that's the whole reason I did this example, is to give you another example of how to find c prime. If we know what c is, we just differentiate coordinate-wise, okay? Just take derivatives coordinate-wise and call it good. Okay, so if we want to do that, the derivative of cosine is negative sine, so this is going to be negative 2 sine t. And the derivative of sine is cosine, so times 2 cos t. So if I plug pi over 3 in, remember, if I plug it in the beginning, remember the sine of pi over 3 is root 3 over 2. So multiply it by negative 2, that gives me a negative root 3. And the cosine of pi over 3 is a half. So that just gives me 1. So we now know that, actually, let me start here. P is 1 comma root 3. And we also know that V, which is the green, say, is negative root 3, 1. And we know that just P plus TV gives me the parametric equations for the line. So we can just finish that off here. So L of T is going to be 1 square root of 3 plus T times negative root 3 comma 1. Which is going to be 1 minus square root of 3t, comma, square root of 3 plus t. And this is, if I want the whole line, I go from negative infinity to infinity. And why don't we just go ahead and, since we got GeoGebra here, right here, let's just go ahead and sketch that. So I'm going to get rid of this curve, these points. I don't think I want to see any of that, to be honest. So I'm going to have a new curve, which is just the circle. So that's 2 cos t, comma 2 sine t. T goes from 0 to 2 pi. And that gives me this circle, right? So I'll kind of move that up, call that good. And now the line, we found parametric equations for that. That was 1 minus squirt of 3. And then you got to get it out from underneath the square root sign times t. So you got to hit the right arrow. And then it's going to be square root of 3. Get it out from under the plus t. And I'm just going to do t as my parameter and go -10 to 10 just to make it big. And what you see is it really is tangent to the curve. So all this algebra that we're doing gives us exactly what we want geometrically. And we can emphasize the point of tangency just by plotting it. That was 1 square root of 3. And then it appears on your plot. Right? Any questions about that? So this is a nice example that allows you to use calculus a little bit, as well as how to parameterize a line, right? So remember, to parameterize a line, there's 2 pieces of information you need: a point on the line and a vector in the line. And that's good. Okay. Okay, so I want to do one more example that relates everything, that uses dot products in order to answer a question about parametric curves. Okay, so we had just gotten finished talking about dot products, right? So I want to let C be the exponential curve. Let C of t be this e to the t cos t, e to the t sine t, right? I want to show that the tangent vector to this is always makes the same angle with the position vector. Show that the tangent vector to C t. So that just means, well, okay, always makes the same angle with the position vector. C of t. Oh, actually, I'm going to, with the position vector. Okay, so let's just highlight a couple things. The tangent vector to C of t really just is C prime of t, right? The position vector really is just C of t. Okay. So geometrically, what I'm asking you to show is that if you have this exponential spiral, right? If you give me any point on there, oops, and look at the tangent vector there, that angle will always be the same, no matter what. This angle between those vectors will always be the same. Now, usually you don't think of the angle between them this way. When you think of the angle between two vectors, you have them start at the same spot. Okay. So usually when you talk about the angle between vectors, you have them start at the same spot. So you might be looking at that angle there. So that angle there is constant. It's independent of where I am on my curve, no matter what place I am. So for instance, if I happen to be at this point on the curve, so that that's my position vector, I translate that to be at the point on the curve, and I look at the tangent vector there. And this angle here has to be the same as the angle back there. So I'm really just trying to say that theta is constant, i.e. show theta is constant. But that's the same as showing that cosine of theta is constant. Oh my goodness. And the thing about the cosine between two vectors, we know that that's just u dot v over the length of u times the length of v. And so my vectors, I want one of my vectors to be c of t, and I want one of my vectors to be c prime of t. Okay. So basically what I have to do is I have to find the formula for c prime and for c, plug it into this and show that it's independent of t. It doesn't matter what t value you get, the cosine of the angle is always the same. Okay, so let's do that on the next page. So I'm going to have c of t is my e to the t cos t, e to the t sine t. So if I'm finding c prime of t, I got to use the product rule, right? Got to use the product rule. So the product rule says it's the derivative of the first. Okay, pop quiz. What's the derivative of e to the t?
Isn't it e to the
Just-
t?
Yes, good memory, good memory. Okay, so it's the derivative of the first times the second. So that's just going to be e to the t cos t plus the first, which is e to the t, times the derivative of the second. And the derivative of cosine is?
Negative sign.
Yes, excellent. So we're going to throw a negative in front of here. So it'll be minus sine t, right? And here it'll be the derivative of the first, which is just e to the t times sine t. plus the first e to the t times the derivative of sine t, which is cos t, right? Okay. Now it's going to make our lives a little easier if we pull out the common scalars, right? So c of t is e to the t times cos t sine t. Definitely thinking of these as vectors now and pulling out scalars. C prime is e to the t and then cos t minus sine t, cos t plus sine t. I know I changed the order there, but there you have it. Okay. And what we have to calculate, remember, is c dot c prime over the length of c times the length of c prime. So let's go ahead and calculate some lengths. Okay, this is cookbook math, right? Step one is get the ingredients. So I need the length of c of t. So that is the length of e to the t times cos t sine t. And I'm definitely going to use some of what we know. We know that this is just a scalar multiple, and in general, you can't just pull the scalar out. And the reason you can't just pull it out is if this is a negative number, there's never a negative length, right? So you can't just pull it out. However, what do you know about E? That's always positive. So since it's always positive, I can just pull it out and I get this. Now, pop quiz, what's the length of cos t sine t?
1.
That's just 1. Those are all the points on the unit circle, right? So this is just e to the t. So the length of c of t is equal to e to the t. Okay. The length of c prime of t is a little bit yuckier, right? It's going to be, I can again pull the e to the t out, and then it's times this cos t minus sine t, cos t plus sine t. And now I'm just going to brute force it, okay? This is e to the t times the square root of the sum of the squares of these guys. So that's cos t minus sine t squared plus cos t plus sine t squared. There's nothing fancy, just painful. This is just painful algebra. Definitely best done in the privacy of your own office, your own home, your own coffee table at the coffee shop. Don't share this with friends, right? Don't do this in public. So the next thing you do is you square this out so that you'll get firsts gives me cosine squareds, outers and inners gives me minus 2 cos t sine t, and lasts gives me plus sine squared t. Okay. The next one I get another cos squared t, then I get plus 2 cos t sine t, then plus sine squared t. And what you notice is the terms with the mixed sines and cosines cancel because they appear with opposite signs. Oh, this is cosine squared. I'm sorry. This first one should have been cosine squared. And what's left is 2 cosine squareds. So this is e to the t square root of 2 times cos squared t plus sine squared t. Because I get 2 of each of them, right? I got 2 sine squareds and I got 2 cosine squareds. So there's my 2 cosine squareds. There's my 2 sine squareds. And cosine squared plus sine squared is 1. So this is just square root of 2 e to the t. Whew. So now we got the ingredients for our formula, right? Our formula said I wanted u dot v over length u length v. That's really the cosine of the angle between them. So I'm just going to calculate that on the next page. So step 2 is use the recipe. This is right? The recipe says that the cosine of theta is going to be c of t dotted with c prime of t divided by the length of c of t times the length of c prime of t. So we can do this. C of t is this e to the t times cos t sine t. So this is e to the t times cos t sine t. I have to dot that vector with c prime of t. And c prime of t we got here is e to the t, and then I get a cos t minus sine t and a cos t plus sine t. All right. So this is going to be another e to the t cos t minus sine t cos t plus sine t. That's all divided by an e to the t times the square root. Now this is just times the square root of 2 times e to the t. And so you with this you can factor scalars out, right? So you're of the dot product, so your e to the t's are going to cancel. You're left with a square root of 2 in the denominator and just the dot product in the numerator. So that's going to give me cos t times cos t minus sine t plus sine t times cos t plus sine t. And that's all over the square root of 2. Right? Because all you're doing is you're multiplying the same coordinates, right? Okay. All right. So now remember what we're trying to show. We want to show that this angle is always the same. So I want, and the idea was to show that the cosine of the angle is constant. No matter what t is, the cosine of the angle is always the same. We've done some pretty horrendous calculations, boiled it down to here. This cosine should be just a constant. It still has t's in it, so we're hoping that once we distribute and recombine, we just get a constant out. If we get a constant with no t's in it, that means it doesn't matter what t is, I get the same angle everywhere. Okay. So let's just finish this off. So I get cos squared t minus, oh my goodness, come on, Raul. Cos squared t minus cos t sine t plus sine t cos t plus sine squared t. That's all divided by the square root of 2. And you know, the mixed terms disappear once again. You're left with cosine squared plus sine squared, which is just 1. And that's just 1 over root 2. So the cosine of the angle between them is always 1 over root 2. Which, by the way, is the same as root 2 over 2. That might look more familiar. So that implies that the angle is always pi over 4. Right? Because the angle whose cosine is root 2 over 2 is pi over 4. What I like about this example is it just relates what we're talking about now. So parametric curves and tangent vectors and derivatives with parametric curves to what we've already talked about, which is dot products and angles between vectors and things like that, right? So this is a very special curve, okay? It is very unusual for that angle to stay the same all the way. Like these kinds of curves, these kinds of exponential spirals, there are parameters you can throw in there and still get the same angle. It just won't be pi over 4 anymore. You can make it so it was pi over 6. You make it so it's any angle you want. It's just that the algebra gets uglier in these other cases. Okay, so let's take a look at how we might visualize this. Okay, so if you want to go along with me, let me see if I can redo this so that you can do this yourself. So if you go to GeoGebra, I'm just hoping this works. So the first thing we have is the curve, right? So the curve is going to be there. And it's going to be our exponential curve. So it's e to the t times cos t e to the t times sine t. And let's just go from -5 to 5. So t goes from -5 to 5, and that gives you a nice curve, okay? Then we should probably get a slider in there. That'll go from -5 to 5. And now let's see, we want a point on the curve. And so a point on the curve is always of the form e to the s times cos s, sorry, e to the s, oops, not s, e to the s times sine s. So that's a point. And you can see that that is on the curve. And now we want our tangent vector. So our tangent vector is going to be e to the s times, for the x coordinate, hang on, let me see what it was. It was cos s minus sine s. So this is going to be cos s minus sine s. So that is my x coordinate, and then my y coordinate is going to be e to the s times, in parentheses, sine s plus cos s. Okay, now this looks wrong because this vector at this point is has its initial point at the origin. So what I really want is to translate the origin. So I'm going to use the vector command. I want to translate the origin to A and B to A plus B. And that gives me my tangent vector. And I'm going to make B disappear because so that really does give you your tangent vector to the curve. And now remember that you want to translate everything so that it starts at A. So that means I even have to take the vector A and translate it so that it goes from A to 2A. So I got to translate everything. So what our calculation just showed is that the angle between those two vectors is pi over 4. That's the angle between those two vectors. And since we have a slider, we can slide it along. Here, well, I guess I need to move this down. We can slide it along. You notice that their lengths change, but it's at least believable that the angle stays the same throughout. It doesn't look like they're changing or waving or anything like that. So it gives you a nice geometric illustration of the algebra that we just did. And without the algebra, we wouldn't have this nice clear picture. Okay. And you can definitely, I mean, you can play around with this and scroll in and make sure that this vector doesn't get too crazy, even when it starts tightening up right down here. You just bring that out. And it really does give you the impression that that angle stays the same. They're just stretching as they rotate along. Okay. All right, guys. I think that's all I really have time for. I was going to do parametric surfaces too. Maybe I'll just mention that briefly when we get started next time, but that won't be on the final, but just so you know what a parametric surface is. And other than that, we will also review for the final on Thursday. Okay. All right, guys, have a good couple days. We'll talk to you soon.
See you.
Thank you.